So we'll get started here. Today's presentation we have titled by A Bumpy Road to Driverless Cars, Challenges and Opportunities. And with us today is Dr. Asad Khattak, who is a Biman Distinguished Professor of Civil and Environmental Engineering at the University of Tennessee, Knoxville. He's the Associate Director for the Collaborative Sciences Center for Road Safety, which is a National University Transportation Center based at UNC Chapel Hill. His research focuses on various types of innovations related to intelligent transportation technologies, transportation safety, and sustainable transportation. Dr. Khattak received his master's and PhD degrees in civil engineering from the Northwestern University. He serves as the editor of the Journal of Intelligent Transportation Systems. So without further ado, I'll let Dr. Khattak start his presentation. We'll hold off on questions, and then once the presentation gets done, we'll have a question and answer session. So, Dr. Khattak.
Thank you, Emil, and thank you for inviting me. I do want to mention that Emil is my more handsome brother. He's also stronger, and I'm delighted to present what I've found over the years on driverless cars. So let me just thank overall the whole Nebraska, University of Nebraska for doing such a good job in terms of their transportation center, but also in terms of broader impact on the field of transportation over so many years. So with that, I want to mention some of the research questions that we'll try to at least explore. How can driverless cars change the future of transportation? What kind of potential do automation systems have for vehicles in particular? And what are the promises, challenges, and policy issues? And also, what are some of the related solutions that come to mind, which would be more like smart growth and also looking at electrification and shared rides? So we'll talk about that concept called ACEs. So let me move to my next slide, which is to try to at least pose a few research questions. Can automation better meet the needs of travelers and also freight, of course, but which I will not be able to talk much about, but I think it's a very interesting and nice area, and early adoption of automation may happen more in truck platooning and also first mile, last mile type deliveries. But putting that aside, what will the transportation system of the future look like? We need to think about that. We may not need such huge infrastructure in the future. Also, how can transportation authorities maximize the benefits of connectivity and automation going forward, and maybe all the associated things that come with that seem to come with connectivity and transportation, which is electrification, for example. So most of us are probably familiar with all the different levels of automation that SAE has put out, and NHTSA also has adopted, which is that level 5 represents a situation where a person can go to sleep in the car, and some say that's just an ideal that would be never achieved. But before that, certainly level 0, we have some kind of maybe some level of automation where we get a warning about an impending collision, and then we progress through different levels where the car takes over control. So in a sense, we have a choice. We have some kind of benefits associated with integrating automation and connectivity of vehicles. And, it is being enabled by the growing computational power, the ubiquity of ambient sensors and data, and artificial intelligence, of course. And, in terms of how we look at cities, we certainly have a choice of becoming more accessible, safer, energy efficient, and cleaner, and supportive of diverse travel needs as we go forward. Sorry, I need to turn on my pen. Okay. And in some sense, we have a choice. This graph shows this figure shows the single vehicle occupants going through a city, and then also a city where even the energy is locally produced, and then also we have diversity of modes, and people have more compact developments, more mixed use kind of environments, and maybe people can use these alternative modes much more. So, this can be enabled through these different cyber-physical systems, that is digital and physical road infrastructure. And we will explore some of these choices we have for going forward. So, what are the opportunities? Well, the idea is that these will serve as economic engines and help us, redevelop in a different way. For example, the parking. We may not need that much parking anymore as we go to higher and higher levels of automation. And therefore, we may even change the structures of our residences if we don't need as many cars, but also redevelop parking areas and also commercial areas that might not need so much space for parking cars. Also, there's a report by McKinsey and Company that estimates these benefits of the economic benefits to be in the 850 billion range within a short period of time. And the way that they think we can capture these benefits of shared autonomous mobility is through integrating AVs with the existing transit system and transportation system in general, also for capital planning for an uncertain future, optimizing and redefining the curb, which I'll show you a little bit on further on, and redeveloping off-street parking into maybe buildings that can be used for other purposes. For example, they can be transformed into offices or residential, and also rethinking of road construction and maintenance going forward. So this is just an example of the curb. So there's a blind pedestrian who is able to communicate with the vehicles and also bicycles that might be coming along the way. And this would require maybe, on a wider scale, redesigning and also pick up and, and drop off of folks from the curb. So this might require pretty big changes in our system. And so the potential benefits are that automation can enhance the current state of transportation by improving safety and mobility. And also in terms of safety benefits, it can reduce the human errors and injury and fatality. We know that the cost of injury and death and property damage adds up to about $1 trillion, the social costs of crashes. So that's a huge cost to try to reduce and a huge challenge basically to try to address. The mobility benefits also include adding communication, which increases road capacity, reduces congestion, vehicle operating costs are also reduced through automation and connectivity, and also providing access for elderly, for people with disabilities, for younger people who are not currently able to travel. So all that is our potential benefits. And then an important point is to look at a new infrastructure design. So this figure shows, it's a little small animation here, where we may not need so much infrastructure, and we can maybe have a smaller footprint in the future in order to capture these opportunities, and to maybe we need to think about the legacy infrastructure that we've been building, and we are putting even more money into it, but which is a good thing. But at the same time, as our system evolves and as we get more and more automated and more and more electrified, as we adopt electrification, we will need maybe a different kind of infrastructure. For example, the people have invested a lot of funding into electric vehicle infrastructure. So, that is something to think about and foresee. So this is a vision of the new infrastructure, but of course we have resource challenges, and we have a lot of inertia in the system, which often prevents us from investing and thinking about how to change things. And through, I think, careful systems planning and jurisdictions and agencies and private sector coming together, we can better meet the needs of people and goods movement by redesigning our system. But this has to be done taking into account the vision that how these systems would evolve. And that vision, although is in some sense easy, but in other sense it's very difficult, because there's a huge amount of uncertainty associated with it. Some of the early evidence of level 1 and 2 automation shows really, really promising results, okay, in terms of safety. So IIHS, the Insurance Institute for Highway Safety, has provided this information, which is very telling, that they have noticed a reduction in claims, insurance claims, when cars have forward collision warning systems. For example, the reduction in crashes is 27%, and injury crashes are also reduced by about 20%, and so on. You can see forward collision warning with auto brake would have even better impact in terms of 50% reduction in front to rear crashes. And blind spot warning and other kinds of systems that are already in, you can purchase them. One has to pay a little, a higher price for such cars, but you can purchase these systems in some of the cars that are available. For example, Nissan Rogue has a good system that can be purchased currently, and so do other manufacturers, especially the luxury vehicle manufacturers. So, the question is, are AVs going to be safer than humans, and will they avoid a collision? Now, that may not be sufficient, because, the tolerance for AV hitting a pedestrian is very different from the tolerance for a human hitting a pedestrian in a vehicle. So, but the premise of these systems is that AVs will detect pedestrians of all types, and notice that there are complexities involved, and these systems are imperfect, and they can miss, the AI systems can miss pedestrians. Now, there are 6,000 pedestrian deaths every year, and I've done a lot of research on what and why, and I won't go into the details of what and why these kinds of crashes happen, but certainly, some errors are made by car drivers in terms of not being able to see or not paying attention to pedestrians, and then pedestrians also could be darting out or having unexpected behaviors that result in crashes and fatalities. But the premise is that we will be able to detect pedestrians of all types, whether kids or older adults, and stop for these detected pedestrians or somehow avoid the collision. And this requires identifying and mitigating the risks caused by difficult to detect pedestrians, and it points to the edge cases, so to speak. And we can see that in this video here how difficult it might be to avoid these kinds of sudden movements. So what is the evidence? And if evidence is difficult to come by, we've looked at some of the results of detection and avoidance by pedestrian collision avoidance systems. And I want to share some of those results. But analysis of these different pedestrians in challenging situations itself is very difficult. So here is some experiments that pedestrian crash prevention systems, that the cars that had these systems did with IIHS. They had 2018 to 2021 model year cars, 92 of them with different makes and models. They did 3,000 tests. And the key results are that notable improvements in performance of this pedestrian crash prevention systems technology were observed over time, that car companies were improving their systems. But there are, I'll show you some evidence that there are, they are not performing as well as one would think, even in these conditions of more laboratory type, and real life tend to be far more complex, for example. So the factors that did affect, which we found, were the maximum deceleration rate of the vehicles, and also the vehicle weight was important in detecting and stopping for these pedestrians. And as you can see here, at these speeds, different speeds like 60 kilometers per hour into the 2018 model year cars, they were able to only avoid 20%. Now, over time, they are going to almost 50% avoidance. So in some sense, that has this has been improving the technology, but overall, at lower speeds, of course, the performance is better. As you can see here, and then I guess one can say that this has certainly improved over the years, the technology. But at the same time, we've seen many collisions, like the fatal Tesla crash in Florida, where it just could not detect a large truck, which was a lateral movement in front of this vehicle, and it, the forward collision warning system was not able to detect it, and the car went underneath a truck. Similarly, a pedestrian was hit when at night when she was carrying a bicycle and crossing a road in Arizona. And there are many examples of crashes like that, which have been investigated in detail. But, these are issues. There are about maybe 100 or so Tesla fatal crashes that we are looking at. So this is just a snapshot. We are still working on this paper of Tesla single vehicle fatal crashes across the world, and in 17% of the cases, autopilot was used. The autopilot malfunctions, which were detected, and so sorry, I am getting distracted a little bit. The autopilot malfunctions were in the area of could not handle hydroplaning and faulty warning systems. And the pedestrians were also involved in some of these fatal crashes, and pedestrian crash prevention systems in autopilots can be improved a lot based on what we've been looking at. Also, when autopilot is not engaged, speed is a key contributing factor. And fires were also noticed in these cases. So that's been a problem. Also, I think it's important that we look at the current state of CAVs, and there's a lot of pilot testing of high automation levels of AVs on public roads. 67 manufacturers are testing these systems in California. The market availability of low levels is pretty high, these adaptive cruise control that I mentioned. And also, there's a bit of a problem with 5G versus DSRC communication going on, but that's one of the issues with the Federal Communication Commission wanting to take away some of the bandwidth that's used by DSRC. So the bumps along the road are that, the sensor systems would, they can fail in bad weather conditions, unseen traffic conditions, road signs not being clearly visible. Also, perception of the automation system can be brittle. That is, the algorithm does not adapt well to situations in which it wasn't trained. Artificial intelligence has its own further imperfections like overfitting, mispredictions, and also sudden changes. And trajectory control could have some issues like vehicle capabilities are degraded in certain situations. And then there's cyber attacks, policy and regulation that's not being put in place, and also social acceptance, whether we are going to have these systems accepted or not. And as you can see, things can change pretty rapidly here. And, all the sensors, which consist mainly of cameras and LiDARs and radars, and these are, plus we need GPS coverage and a few other things, but that's mainly, the computational power has to be present in the vehicle, but those are not huge challenges, but the challenges are more in terms of the processing of the information quickly enough to deal with complex situations. And for that, Professor Koopman at Carnegie Mellon has given a good description of the design domain, operational design domain, where highly automated vehicles could operate and can operate. But they are faced with a lot of complexity in urban areas, in particular, like roadway geometry, signs, markings, pedestrian zones, debris on the road, police enforcement. Those are unusual situations that are hard for AI to learn. And also traffic rules and behavioral constraints. Local customs may vary as to who takes a left turn. There's all kinds of issues with communication between pedestrians, for example, and cars, and also a digital infrastructure like DSRC and dedicated short-range communication devices, GPS availability, as well as the different users. We have a lot of different users, including horse-drawn carriages, and also vulnerable users, people with disabilities, and so on. So I think that along with the weather and changes in tree leaf colors and sun angle, and maybe football games represent a different situation with tailgates and so on, and all that could be bringing in the complexity, and therefore these vehicles can only operate in certain under certain design conditions where they can they can be safe. Now, one of my colleagues, Dr. Chakraborty, has been working with me on looking at different situations from California that, it's public information, and we can actually do very detailed simulations of the crashes that have happened, but also to look for edge cases. So, for example, we simulated in, I think this was in Carla simulation, whereby you can actually go to simulating the radar and LiDARs. And so this is the LiDAR image. I wish I had time to show you all the animations, but basically what we are able to do is to actually, look at what happened in one particular crash, but also to change the conditions and make it, let's say, raining or dark for the same situation, and then see what will happen. So it can help us a lot in terms of that edge cases. Also, throughout the country, people are engaged in doing pilot testing, and Tennessee has also been doing this, which is critical, I think. But at the same time, we also need to pay attention to the policy issues being, important going forward if these systems are to diffuse. The best practices for AV design, testing, and deployment need to be shared. The model state policy, which there are documents of along those lines issued by a federal government, where AV issues fit into the regulatory structures, and also these would include expedited review of exemptions like human subjects issues when we are doing testing, and this may spur, AV development. And also new tools are needed and have been suggested for AV deployment, like expanded exemption authority and also pre-market testing to assure that we have a safe AV before it's being sold. The issue here is that there's no certification process. That is, if we fly an airplane, the airplane usually would have to be it always has to be certified by federal authorities that this is safe to fly, and they go through a rigorous process in that certification. But for AVs, we don't have that certification process. So that's I think a pretty big gap. In terms of policy issues related to CAVs, I wanted to mention that there are huge issues here, but I'll only be able to go through some of them. For example, who pays when a driverless car crashes? And liability, shifts to software developers and vehicle technology, because that's what was driving the car. And insurance rates currently are based on, performance of the individual driver. So the elimination of the driver calls for new definitions and clarity in the legal framework for this. Similarly, issues arising from possible disruptions caused by CAVs, like infrastructure and transportation funding, could be affected, especially with movement towards electric vehicles and also automated vehicles. Roadways may need significant changes to accommodate AVs, and methods for funding for those investments need to be figured out and may need changes. Right now, we have the money is basically coming from fuel taxes. Also, vehicle-to-vehicle communication, well, we see there's a lot of hope that, these crashes, up to 80% of them are preventable, but are any crashes acceptable by AVs is the question. And, clearly, that one crash of a pedestrian and an automated vehicle has received a lot more attention than the 6,000 deaths that happen every year. So in some sense, that might indicate that as a society, we may not be willing to accept AV crashes even though they may be on average much safer. Also, cybersecurity issues are hugely important, and we are generating more and more data, and then which leads to this issue of data privacy and ownership and hacking of CAV data. We have also done some analysis of state policies and looked at 78 state policies from 36 different states and Washington, D.C., and also synthesized legislation by different definitions and, all the way to registration and titling and first responders and so on. So the key results were that we ranked each state against the US DOT model state policy, which should have, clear definitions of these issues that are mentioned here. And state policies are the driver of these testing, operation, and deployment of AVs. And certainly California leads in terms of, having a lot of documents that are policy documents about simple things like, what are the seat position requirements for an operator or a remote operator, okay? And also restrictions for operation domains, what level of vehicle operate, and how do we expand those domains, okay? The other, issue, for example, is law enforcement, and how would they know that the driving task was being performed by the automated system or the humans? It's not so easy to figure it out, especially if they have to respond to 6 million crashes a year. So those are some of the interesting issues that emerged, and we did some text analytics on these documents and found that, of course, NHTSA and ADAS technologies and operational design domain were discussed along with insurance and liability issues. But, as a societal issue, we need to address all these complex issues. Of course, this bill keeps on hammering, it keeps on getting delayed, but the point is that, it does have a lot of investment in electric vehicles and modernizing the bridges, highways, roads, and main streets, and improvements to existing routes and expansion. So, I think these numbers might change, but the point is that these are priorities. And certainly, I think the concept of automation, connectivity, electrification, and shared mobility lies within this infrastructure plan that the administration has. So just to kind of maybe clarify a little bit the difference between autonomy and connectivity. So some systems can be both highly automated and highly connected, like automated highway systems. There, we would have the vehicle communicating with the infrastructure and also other vehicles, and they will be fully cooperative. So this is the degree of cooperation, this is the degree of autonomy, and at some level, the military vehicles that might be going in a desert would be considered as really, they are not talking to the environment, but they are able to go through and navigate the terrain. So that is an example of an automated system. On the other hand, these cooperative collision warning or platooning systems are kind of a mixture of autonomy and cooperation. So I think we need to pay close attention to how we can achieve these goals. And also within the context of electrification and sharing, shared mobility being coming under some pressure in recent days due to social distancing and the COVID. But this is a solution that we can probably have for and and implement in smart cities. That is, the connectivity helps us reduce the road crashes, the maximizing operating efficiency of these vehicles. Electrification takes us away from fossil fuel dependence, as well as reductions in emissions, which ultimately are causing huge damage to the environment, and also reductions in noise and also operating costs. Shared mobility, of course, reduces the fleet size, reduces travel costs, provides accessibility for diverse populations. And automation, like I've mentioned, reduces the parking demand, as well as roadway infrastructure footprint, and improves congestion, as well as reduces operating costs. So all that has been kind of encapsulated to some extent in one of these surveys in California that it's I think it's called California Vehicle Survey. And there they found that this level 2 type automation, these are stated preference questions, but they indicate that there's a lot of interest, and about good 65% of the respondents were interested in this. But for self-driving cars, which are more like level 4 and 3 automation, there seem to be concerns and less interest. But still enough of the population said that they are interested. And we did a bit of analysis of this and presented a paper at TRB where we looked at high levels of automation, alternative fuel vehicles, car sharing. And, a lot of people just wanted, maybe these 2 levels of automation and were not that interested in alternative fuel vehicles, but some were just interested in low levels of automation, as you can see here, the percentages. It seems like only very few people actually were totally interested in all of these together. So kind of gives us a little bit of a pause about how successful these systems could be. And also in terms of quantifying CAV impacts, we have done some research, which I wanted to share quickly with you, where we looked at ACC and CACC and see what kind of benefits they can bring. Cooperative adaptive cruise control is where the front vehicle communicates with all the vehicles, where adaptive cruise control, each vehicle in front communicates with the one in the back. And we looked at karma data to see how these impact safety, mobility, and also energy and emissions. So there is a clear sense, if you look at speed, that the ACC has more volatility. This is a platoon of 5 cars, whereas when you have the cooperative adaptive cruise control, this would be much more reduced compared to the volatility that we see here. And this is not even like 5 cars following each other with no automation. They have some automation here, but still we see much improvement when we add the cooperative part. And similarly for accelerations, you can see that, those are much less, jerky, and we are able to see clear benefits. So Iman, one of our students, did this study. It's been published in TRB, and basically found that, this fuel consumption, we see reductions of 3 to 7%, 6%, but this is compared to already automate some level of automation. So similarly, emissions also saw reductions, as shown here. And also we've looked at how cars can be integrated, these automated cars, and interestingly, found some data from Texas A&M to look at, if you are following an adaptive cruise control vehicle as the leader, your behavior also is a little smoother. Okay, so it seems like we found that drivers following an AV had lower driving volatility and higher and safer times to collision, and also they consume up to 11% less fuel due to the due to the stability of movement. So in terms of research questions that I posed, I wanted to say that, we want to be able to say, maybe in terms of automation fitting into the needs of travelers, yes, certainly, we are seeing early evidence of safer movement of vehicles. And IIHS evidence shows clearly that there are benefits. The karma studies show that certainly we are reducing the volatility, we are making the flow smoother, and we are able to provide those benefits to travelers who are willing to adopt these systems. Also, what will transportation system of the future look like? So certainly, giving us a little bit pause, like I was mentioning, is this interest from the survey that we found for all of these together. Maybe the society is not interested in all of them, but if you think about customizing these to different portions and segments of the society, then that interest is there, and there will be significant market penetration of these systems. It just is also dependent on how well our AI systems are developed, how well our sensing systems are developed, and how well our control systems are able to control these edge cases, edge situations, and not result in crashes or fatalities. Also, how can the transportation authorities maximize their benefits? And I think that is through these test beds, research, development, and deployment, and harnessing the big data using AI. But also, I think regulation is extremely important, and we need clarity in all of our states to be able to address I guess diffusion of these systems in a responsible way and in a good way, and I think there's a lot of potential there for improvement. But those are the methods by which I think we can achieve these goals. So I hope this has been somewhat useful to you, and thank you for attending this talk, and I'm happy to answer any questions if I can.
So thank you very much, Dr. Khattak, for the presentation. During the presentation, we asked the attendees if they have questions to send them via the chat. So I see that there's some questions or comments in the chat box. So I'll go over there and so the first question that we have is, are there technological safeguards to ensure that the autopilot can be disengaged, which implies that the driver has control, if the system fails to detect a dangerous situation?
Yes, that's an excellent question. So, in fact, one of my PhD students, Ellie Boggs, wrote a paper, which we'll be happy to share, on disengagements. And, luckily that data is available in California. So as companies are testing their products, there are, this includes Apple, this includes Waymo, it includes the 60 or so companies that I mentioned. So that, there's always, some way to intervene. There's no level 5 automation currently in the system that's being tested, at least on roads. The driver always has the ability to intervene. And in fact, we've seen, we've analyzed that when they do intervene, it may be preventing some of the crashes or lowering its intensity. But disengagement itself is, sometimes the car will suggest that it cannot deal with, so it has intelligence to suggest that I cannot deal with this situation, just you need to disengage. Or the driver may feel like, the car is going too fast for the conditions and then be able to disengage. So that is always an option. But when crashes happen, was it disengaged or not? And that's a fundamental question. And also, how much before did the person intervene if there was a crash and took over control but wasn't able to still prevent it? So who's going to be liable in that case? So those are all the interesting issues that come out. So basically, yes, the user can disengage the system. I'm not aware of a system that cannot be disengaged by the user, but when and how and if they should be disengaging is the issue, which is far more complex, because when once you are in automated mode, people get distracted. People when they're not in automated mode are distracted. So in that case, their ability to come back and look at the situation and then respond to it is it's a big human factors question.
Thank you. The next question is that autonomous vehicles may be able to drive in one area, but may be poorly equipped to function in a different area, implying that traffic and road conditions may be different. So how will this problem be tackled?
Right. So that's the operational design question. So basically, right now, it's up to the states to decide. Okay, this is where we will do testing. So Waymo, for example, is doing actual testing in Arizona. Okay. So, but they are restricted to a certain neighborhood or a certain area. For high levels of automation. Now, how do we expand that is the policy issue. Do we let these cars, highly automated cars, operate in, without certification in, highly dense, maybe urban environment where the chances of, hitting a pedestrian or chances of, maybe hitting a person with disabilities are much higher, then there we need to, society has to decide, and we haven't tackled this issue of, okay, how do we expand this design domain to those places, and what are our criteria, and do we need certification before we do that? So those are unresolved issues which we need to discuss and maybe have a dialogue around. But it seems like there are so many different issues associated with this automation that people seem to have maybe not paid a heck of a lot of attention to this operational design domain issue and its expansion.
Thank you. The next question that we have is, how vulnerable are the AVs and AI to cyber attacks? And I know you had something on cyber security on one of the slides.
I mean, currently, from what I understand, they are pretty vulnerable. there are protocols and companies that do provide some level of security for, especially when they are exchanging information with the infrastructure. But we looked at some of these technologies that might be helping enhance this security, and we didn't find that much in terms of whether research or private sector companies providing support for these vehicle-based technologies. But I think there are a lot of developments in the computer science industry where we can take advantage of that. But things that like handshake by the DSRC equipment, and how that happens between, let's say, in-vehicle unit and roadside unit, and how securely we can transmit that, and how much, whether the packet, can be intercepted and midway and or at the source, and changed. Those are all issues that have not been at least to my knowledge, addressed or resolved. So that's a concern.
Thank you. Another question is, there's often give and take between driver and pedestrian. So I've experienced this many times. If there's some ambiguity about a situation, the driver may gesture to the pedestrian to move forward or something to that effect. So there is some level of communication with eye and body between the users. And the question is, how would automated vehicles deal with that, or take into account such communication? Is it possible to take into account such communication?
It is possible, but to my knowledge, I don't know if anybody's done it. So, for example, if the AI can read certainly the movements of the person, and those kinds of rules of behavior or engagement, and those might be very localized rules. In India, maybe it's different than here, or China might be different. That communication that happens. But those behavioral part, we can make AI systems be trained to recognize those gestures or those movements. But again, that is a humongous task to do, and then program it into the vehicle, and then let the vehicle decide, okay, this movement, this pedestrian was trying to say this to me. So, that would be a very interesting research that one can do. But again, those behaviors may also be changing. That is, the pedestrians, when they sense that this is an automated car, might have a different gesture or different behavior. In fact, people were saying that they may be just coming out more aggressively, assuming that the car will stop. But as I was showing you, these cars, the current systems cannot stop. So it's an issue, and I think to some extent it would be good to be able to understand this communication, but it's risky at the moment, and I don't think that there's a lot of work going on that topic. Or if there is work by auto companies, then they are not really totally sharing it.
One other question that came in case of emergency vehicles where they do not follow the typical rules of the road, how would an automated vehicle know to, for example, yield or behave accordingly?
Right. So those are the things that we need to be programming. Those are the edge cases that we need to be programming and understanding that, okay, or on Halloween night, people might look different, So in some sense, those pedestrians that we see on the road might be looking very different on Halloween night, or like was said, the emergency vehicle is just not behaving the way that, or the police car might be standing and blocking a road, and it has to recognize that, or the pedestrian is a flag person, so all of these edge cases have to be programmed into the intelligence of the AI that we are all these car companies have developed. But this is non-trivial, and that's why it's so complex, and that's why these systems have not diffused as fast as we thought they may, because those are situations where things are not operating normally, and therefore a human intervention might be needed. And or even if we program them, it may not be easy to for AI to deal with the complexity of different EMS situations. So that's the thing. They are rare to start with, and within that rarity, there's a lot of variation. So that's the issue.
Okay, I'll ask the last question since we are coming up on the hour. How does the US compare to other countries in terms of development, in terms of getting automated vehicles on the roads?
Yeah, so I think US has led on the I would say low levels of automation, certainly, and I would say that compared to Europe or Japan or China, I think the US has been at somewhat at the forefront. I think a lot of the research is not being shared by the nature of the proprietary nature of OEMs and their products. But essentially, I think in terms of research, the US has led, and in terms of implementation as well. Some people find it somewhat disconcerting that we are allowing testing for example, in California on actual roads. And if we put restrictions, then companies move to other states. For example, from California, they move to Arizona. New York has the highest, restriction in the sense that for automated vehicle, there has to be a police officer sitting, if it's being tested and on actual roads. But we are allowing that to happen, which is, I think, making the diffusion faster. I think China would be probably close in terms of adoption. Since I'm more familiar with the context in China, but I cannot say that we are in any sense lagging on adoption or on development or on research.
Well, thank you very much, Dr. Khattak. I think the presentation was very insightful. We've recorded this and we'll be putting it on different social media that our transportation center has. So also on behalf of all the attendees, I'd like to thank you. If we were in person, the attendees would be clapping at this point. But
thank you.
Thank you very much, and I hope to see you at TRB. Take care.
Certainly. I look forward to seeing all of you. Bye-bye.